Welcome to lesson 30 of industrial automation and control. In this lesson, we are going to continue to look at pneumatic systems. So, in lesson 30, we will look at more components, pneumatic components. We will look at a kind of logic called pneumatic logic, and we will see some control applications, and finally, we will see a comparison with hydraulic systems. So, and the instructional objectives are firstly to be able to draw some typical valve constructions, describe and or kind of pneumatic logics, explain different functions of some special kinds of valves which are used in pneumatics like a quick exhaust and flow valves, mention comparative merits and demerits of pneumatic and hydraulic systems, and also be familiar with some control applications. So, we have already seen direction control valves, we have also seen them during hydraulics. So, there is nothing much new here. So, the valve is actually shown here. There are, so you can see the inlet and the outlet ports. So, you can see that this is the when the pilot pressure is there, this is, as you can see, that there is a spring here. Let me choose a proper pen here. So, this is the pilot pressure. So, when the pilot pressure is not there, there is a spring, right. Oh, I see, this is selected as the eraser. I have to choose a pen first and then choose this color. So, yeah. So, so it's spring loaded. So, when there is no pilot pressure, then this spring is going to push it up and this is going to be closed. So, therefore, the valve is closed on both sides. So, therefore, this symbol is shown, and when the pilot pressure is applied, then it goes down. So, there is flow, simple two-way valve. Then we come to a three-way valve. Basically, this is a there are two ports, one is supply, the other is exhaust, and again, as you can see, this is also spring loaded. So, when there is no when this is button operated. So, when the push button is not pressed, then this is supply is closed and cylinder is connected to exhaust. So, therefore, when this is pressed, this will open and this will close, this will close. So, these points will close, and the supply will get connected to exhaust. So, that is this rectangle. These are standard, you have also seen them during the hydraulics course. So, we are going little fast on this. So, then we have this is a special kind of valve which is called the quick exhaust valve. This is needed because if you do not use it, then as you said that in pneumatics there is no return line. So, the air is generally released into the atmosphere. Now, the question is, the earlier you release it to atmosphere, the better it is in terms of pressure across an actuator, or in terms of, because the air will not take, because that much pressure will not be required for driving the air through the tubing, and also the time response of the system will improve. So, therefore, these valves are sometimes used when you do not release the air at the direction control valve. The air is driven by the direction control valve, but is released right at the actuator using a quick exhaust valve. So, you can see a construction here where so when you are driving pressure into the cylinder, these are typically connected with cylinders, then this is the basic mechanism. This is the mechanism. So, this is getting pushed up, and when it is pushed, this is closed. So, the air path is shown, the air is flowing into the cylinder. This is coming from the DCV, this is from DCV or direction control valve. On the other hand, when it is coming from the cylinder, when it is coming back from the cylinder, then it does not need to go to the DCV and it is released. See, this will press it, and therefore, this will close and the air will actually flow out into the atmosphere locally at the cylinder. So, it is quickly exhausted, right. So, that was the idea. So, you can see this that so this is an actuator which is being driven. So, what happens is that the air flows, this is the DCV. So, the air flows into this, goes through this and drives the actuator. So, the actuator moves, when it moves it actually expels the air. So, it actually expels the air. So, because this is a pressure driven. So, when this pressure line increases, this valve is going to shift, as we have shown the mechanism. So, then this is actually connected to this and gets exhausted right there. It actually does not have to come back to the DCV. So, this tubing is not used for the return path and the air is exhausted right here. So, this is the function of the quick exhaust valve. You can have similarly, you sometimes you want that for synchronization purposes. You would like that after you put an actuator, there are 3 valves will actually move one after the other. So, if you have to realize this concept of one after the other, then you have to create gradually increasing time delays, after which these valves will be shifted. So, that is done. This is a typical construction. Basic idea is that when air is flowing to create pressure and shift the actual valve, if you just put a chamber on its path, then some time will be required for the incoming air from the pilot to fill that chamber before pressure can develop and shift the main valve. So, there will be a time delay. So, now depending on the volume of the chamber, you can create variable time delays. So, exactly that is what happens here, So, so you see that air, this is the pilot port. So, the air comes and fills this chamber. After this, so pressure builds up slowly because of the chamber, and then it shifts the valve. Then it actually applies the pressure on the spool, and that will shift the valve. So, this is the basic mechanism by which a time delay is created. Similarly, you have flow control valves. So, in flow control valves are mainly used to have a controlled speed of the actuator, especially when it is driving load. So, sometimes as we have mentioned in hydraulics, that sometimes we want that while it is retracting, it should be at high speed to save time, but while it is driving the load, it should be at lower speed. Sometimes for part of the journey it may be at one speed, towards the end of the journey it may be at slower speed, basically because of the fact that the load typically tends to have an inertia, and if you push the load too fast, then a lot of kinetic energy can accumulate in the load and it can go and hit against something. So, towards the end of the stroke there is a need to reduce speed. So, basically the flow control valve is used for controlling cylinder speed, and you can put this flow control valve either in the path of the incoming air or in the path of the outgoing expelling the air which is being expelled from the other half of the cylinder, right. Now, it turns out that generally there is a benefit of these two cases are called meter in flow control and meter out flow control. So, meter in is when you put the flow control valve on the incoming airflow, and meter out is when you put it at the outgoing airflow. So, generally people sometimes prefer putting it in the outgoing flow, because that creates a back pressure which kind of stabilizes the motion of the valve, motion of the cylinder. So, so the moment the cylinder tends to move faster, immediately the flow control valve develops some pressure which tends to decelerate the cylinder. So it's a kind of negative feedback, and it will stabilize the cylinder motion. So the application is shown here. So you see that this I think we also discussed in the case of hydraulics, that while the fluid is flowing, it is flowing through this path. So there is a check valve which is put, so it bypasses flow control valve. So it will go through this path and it will enter here. But while it is coming out, the fluid which is being expelled obviously cannot pass through the check valve, because there is no, this cannot flow this way. So it will pass through the flow control valve and then finally get expelled. So this flow control valve is used to so that when the cylinder is moving this way, there is a certain speed, that maximum speed that it will generally achieve. You can have different flow control valve settings here in these two valves, so that you on two sides you can have different speeds of the cylinder. So okay, so this is the same concept. I mean, sometimes what happens is that you can start oops. So sometimes it happens that you need to for example, take the example where you need to clamp various kinds of objects of various size. So some objects can be large, some object can be small. So you are having an actuator which is advancing, and when it meets the object, it pushes it till it gets clamped with a certain amount of clamping force. So certain fixed decided amount of clamping force. So you can see that depending on the object dimensions, the stroke required after which the required clamping force would be obtained depends on the dimension of the object. So if the object is A, then at this point only that the clamping force will be realized. If it is of the size B, then at this point the clamping force will be realized. If it is C, so how much the cylinder will move and where it will stop has to be determined based on the pressure developed in the chamber. So the pressure will develop, the back pressure will be developed in the chamber when this cannot move again. So you see that there will be this will actually resist the movement. So therefore a certain pressure difference will arise, right. So normally this pressure difference will not arise, and the cylinder will be free to move. So yeah, so actually we can have this law. What I am trying to say is that we can sense the pressures. We can sense the pressure initially. What is the pressure difference? The pressure difference is just enough to accelerate the thing. After that, what is the necessary pressure difference? The necessary pressure difference is just to get a certain amount of clamping force, right. So by sensing the pressure difference across the two ports, one can actuate the cylinder so that it will stop after developing a certain amount of clamping force. That's the whole idea. So you see that you can start at at a certain point you can start shifting, and then as it shifts, the pressure at one terminal will fall and the pressure at another terminal will rise, and then when it rises up to a certain level, then the shifting has to stop, so that a certain amount of pressure is reached across the cylinder. So, yeah, so exactly that is shown. So, you see that you are sensing this pressure A and pressure B, and then you have to use an appropriate logic to actually drive this valve. So that a certain amount of pressure is force is developed. Now, so this is about valves. Now, these valves are can be actuated, as we have seen that we can have various kinds of logic for actuating valves, and not only that we have after. So, basically an electromechanical actuator on one side is going to interface with the logic elements which decide the condition under which the valve should move. So, on the other side, when the valve should move, it should provide the necessary power for the main valve to shift. So, there are two things which are necessary. So, the electromechanical actuator can actually, this providing power, this can be done in various ways. For example, it can be a directly solenoid driven valve where some current is driven into a coil and it pulls the spool. On the other hand, as we have seen in the case of hydraulics also, that it can be directly pilot pressure driven, generally air pilot is used, or it can be, sometimes it can be a two stage thing where an electric signal will drive a pilot pressure. So, there will be some sort of an electric to pneumatic converter, that is also possible. So, there are various ways. Generally electric to pneumatic converters are used because the electric signal can be very simply generated, and we can use computers, we can use various kinds of signal processing on the electric signal, and then finally convert it to a pneumatic signal for the purpose of either for the purpose of safety or for the purpose of higher power, etc. So, very often we have electromechanical actuators. So, electromagnetic actuators. So, basically it works by electromagnetic attraction between a permanent magnet and an electromagnet. So, when you drive or sometimes between an electromagnet and an iron spool, both are possible. So, there could be various geometries. The actuator can maybe rotary or linear, and typically the specifications involve starting force, stroke length, by how much it can move, and the current requirements. So, typically the force varies depending on the current as well as the displacement, because basically it is by flux. So, the flux actually depends on the current, because the current decides the magnetomotive force, and it also depends on the reluctance of the flux path, which depends on the gap, which keeps changing during motion. So, the force characteristics depend on current as well as the position. For example, this is a typical solenoid valve. So, you directly can drive current into a solenoid valve, which will pull the spool. Similarly, you can have electronic interfacing. So, this is a slightly more elaborate configuration. So, you have electric feedback of signals, maybe either displacement. So, you can have position sensors, or you can have pressure sensing, as we have discussed. So, these electric feedbacks come from sensors using some transmission technology. In this case, we have just mentioned 4 to 20 milliampere, it may be something else also, and then they are taken acquired, these signals are acquired in a digital controller. So, finally the digital controller computes the necessary force that must be applied for control to the valve. So, that is output through a D to A converter. These are A to D converters, because these signals are analog. So, they have to be converted by A to D. This is we have just for example, we have shown a sort of just to indicate that it is also possible to use a digital let us say a microprocessor to control these. So, this is the microprocessor CPU and this is the memory. So, the microprocessor finally gives a digital command which is converted to an analog command. In general, actually there will be a power amplifier, because a microprocessor generally cannot drive a coil. So, typically one can use relays or one can use power amplifiers. So, this is the, so finally a current is driven. Once the current is driven, using this attraction principle, this is what is called this is the I2P converter, and often referred to as a flapper nozzle system. So, what happens is that if this current flows, then this will start to move. This is the flapper. This is the flapper. This will start to move depending on the current, and if it starts to move, actually this gap is shown very exaggerated. Actually, this gap remains very small. So, and also what is not shown is that there is also a pilot pressure source. So, there is a pilot pressure source which is a constant high pressure. Now, what happens is that by changing the position of the nozzle, see what happens is that if this nozzle is very far away, then this pilot pressure is going to drop out and go to the atmosphere right here at the nozzle. So, therefore, this pressure which will develop here is going to be somewhere here you have exhaust pressure, here you have pilot pressure. So, the pressure here is somewhere in between. Now, as you bring this closer and closer, you are here you have the nozzle. So, you are bringing the flapper closer and closer. So, you are closing the flapper, you are rather closing the nozzle. So, if it was totally closed, what would have been the pressure? The pressure would have been pilot pressure itself, because there is no exhaust. If it was totally open, then the pressure would have fallen close to the exhaust pressure. So, as it moves and these movements are fractions of millimeters, then you can have a very high sensitivity, high gain variation of the pressure at the pilot port of the valve, and the valve can shift. So, such interfacings are possible for actuating the valves.